We've discussed the definition of integrals as limits of Riemann sums, and we've discussed some of the properties of integrals. And we've seen how difficult it is to actually compute an integral. We're going to now learn how to compute an integral the easy way using the fundamental theorem of calculus. So to develop the fundamental theorem of calculus, we'll use a specific problem to motivate the development. The problem will be how to compute a specific integral, the integral from -1 to 1 of dx over 1 plus x squared. So before we discuss how to compute this, let's make sure we understand exactly what this integral means. One way of looking at it is that it's the area under the curve y equals 1 over 1 plus x squared between -1 and 1, the green shaded area that I'm showing over here. But we know that fundamentally the definition of this integral is a limit of a Riemann sum. So the limit as delta x approaches 0 of a sum of a whole bunch of terms, each of which has the form delta x divided by 1 plus x squared, where we use values x sub j. For example, and n were 4, then we could divide it like the red lines show on the x-axis over here. And our first value for x sub j, x sub 1, would be where this blue arrow is indicating, and we would get an area of a rectangle like this. Our second value would give me a rectangle like this. Our third value would give me a rectangle like this. And the fourth value, a rectangle like this. And the sum of these four rectangle areas would be the n equals 4 Riemann sum, or the delta x equals 1/2 Riemann sum that corresponds to this integral. My four x values are x1 is -3/4, x2 is -1/4, and so on. And I could write out the n equals 4 sum as 1/2 over 1 plus x1 squared, 1/2 over 1 plus x2 squared, and so on. There'd be four terms. They come out to be 1.58, etc. Now the integral is actually a limit of this Riemann sum. Let's see what happens if I increase n to 8. When n becomes 8, then delta x becomes 1/4, and you'll see that all of the numerators here, delta x, are turned into 1/4. And now the sum has gone down a little bit. We're down to 1.5734, and the exact value of the integral is found when you take a limit of these sums as n goes to infinity and delta x goes to 0. When students are first presented with this problem, they think back to when we first had the problem of computing a derivative. And the way we attacked that problem was we computed the difference quotient, and then we actually took the limit of the expression. So it's natural to think that the next step would be to simply compute the summation and then come up with some kind of theorem for writing the summation as an algebraic expression in terms of n or delta x, and then computing the limit of that. And the problem is then you'd have to find some theorem to sum the expression inside the sigma notation. But that expression is going to be different depending on what function you're integrating. And there's no way to find a way of summing every possible function that you would want to integrate. So that method is not actually going to work, and we need a new method. But luckily there's a totally different approach. Now it's a strange thing that sometimes in math, when you have a really tough problem to solve, the good approach is to turn that problem into a much bigger problem. And it'll turn out that the bigger problem is a lot easier to solve than the little problem. And then once you've solved the big problem, you already have the solution to the little problem. This might seem scary, but don't worry. Let me show you what the bigger problem is that we're going to be working on. Here's a picture of the n equals 4 Riemann sum that we were looking at before. And the sum comes out to be 1.58818. And then we could also look at the n equals 5, 6, 7, 8. N equals 8 sum comes out to be 1.57340. The original problem was to figure out the limiting value of this sum as n gets so large that we're basically looking at the area under the curve. Now, as I said, we're going to turn this into a much bigger problem. What is the bigger problem? The bigger problem is, let's find a function of the right endpoint of the region. Let's say we're integrating up to some point I'll call x, and then the area under the curve is small when x is close to -1, and then it gets larger as x gets bigger. If we could find an entire function, which I'll refer to as the area function, then all I would need to do is set the value of x equal to 1 and evaluate the function at 1, and I have the answer to the original question. So that's the bigger problem. Remember, here's the original problem. We want to find this green area here. We're turning it into a bigger problem where we're finding the area from -1 to x, the blue shaded region. That is a function of x. So the first thing that we need to do is figure out how to write an integral expression to represent this function of x, the area function of x. And the first thing that most people think of is the integral from -1 to x of dx over 1 plus x squared. But that's wrong. There's a mistake. Can you see what the mistake is with that expression? The problem is x is being used in two different ways. We're saying an integral is going from -1 to x, and it's an integral with respect to x of this function of x. So we're saying basically that x takes on all the values between -1 and x, and that doesn't make sense. So we need to introduce another value to define a of x, another variable. The problem is we can't make this the x-axis anymore, so we're going to name it the t-axis, and we're going to say this function is actually 1 over 1 plus t squared, and then we integrate 1 over 1 plus t squared from -1 to x. And when we evaluate that function at x equals 1, then we'll have found the original green area that we're looking for. And that's how our larger problem will help us solve the smaller problem. So before we go about trying to find the identity of a of x, I want to point out an interesting property of a of x. And that is that if you look at a of x plus h and a of x, if you compare the two values a of x plus h and a of x, where h is some tiny little increment, delta x, you can see that when you subtract them, you get that small integral over there. Okay, put in terms of integrals, it's just a familiar property of integrals that we already have studied. The integral from -1 to x plus h minus the integral from -1 to x is the integral from x to x plus h. That's going to help us in determining the true identity of a of x. So, how do we find the true identity of a of x? The answer is we're going to set about trying to find its derivative. That is, we're going to look for the derivative a prime of x. And how do you find the derivative of a function that you just made up? You have to start out with the definition of the derivative. So it's the limit as h approaches 0 of a of x plus h minus a of x over h. But we just saw that the numerator in that expression is a difference of two integrals, and that difference can be expressed as a single integral. Now let me represent that numerator of that expression by this little orange region in the figure over here. It's the area of that orange region that I will then be dividing by h. But if you look closely, you'll notice I did not really draw a picture of the region described by this integral. I really drew a rectangle. If you look at the top, you can see it's flat. And you might think that I'm cheating to replace that actual area with a rectangle. But in the limit as h approaches 0, the difference between that rectangle area and the actual numerator of this expression becomes so small that this quantity over h has the same limit as the rectangle area over h. So without changing the value of the limit expression, I'm going to replace the numerator with the area of this orange rectangle. So first I have to identify the height of the rectangle. Let's call it p. Then a prime of x is equal to the limit as h approaches 0 of h times p over h. Now I have to identify the value of p. P is found by looking at the y-coordinate of this curve, and this curve is y equals 1 over 1 plus t squared. At what value of t? It's t equals x. So p is actually equal to 1 over 1 plus x squared. And we have found the derivative of a of x. It turns out that the derivative of a of x is 1 over 1 plus x squared. Basically, the rate of change of the area function is the height of the curve right over the place where x is. And that actually makes sense if you think about it. Let's go back to this picture and think about why it should be true that the rate of change of the area function is equal to the height of the curve. Well, if we're over here, if x is down here near -1, then as I increase x, this is me increasing x, you can see that the area is accumulating, and when x moves up a little bit, then you increase the orange region by some small amount. But when we move over here to x having values near 0, then at this point, when I increase x a little bit, because the curve is so much higher, I add a larger amount of orange region. That means that the accumulation of area is going to be faster. I can plot this function. This point plotted over here represents the value of the accumulated area so far, and when I increase x, that value is going to go up, and you can see that it's accumulating area under the curve most rapidly right over here when the curve is highest. When the curve is lower, it's not accumulating as rapidly. So if you think about it that way, you can see that it makes sense that the rate of change of the accumulation of area is equal to the height of the curve above the right endpoint. Now, suppose we accept that. We now know that a prime of x equals 1 over 1 plus x squared. That's great. Now all we have to do is use our skill at antiderivatives to find a of x. We just have to think, do you remember what is the antiderivative of 1 over 1 plus x squared? It's familiar, isn't it? There was some function we knew of whose derivative was 1 over 1 plus x squared. Can you remember it? It's the arctangent of x. So now we have found the identity of a of x, right? A of x equals the arctangent of x. Uh-oh, but wait a minute. There's a plus c. Now, the whole reason we were trying to find a of x, remember, was so that we could find a of 1, because a of 1 was the answer to the original question. If a of 1 is arctangent of 1 plus c, where c is something that could be any number, we haven't gotten anywhere. We're back where we started. We have no idea at all what the value of a of 1 is. So having the derivative a prime of x has not helped us find the value of a of 1 at all. What we need to do is pin down the value of that arbitrary constant, and in order to pin down the value of an arbitrary constant, we need an initial condition. We need one data point. All right, we don't know the value of a of 1, but do we know a of something else? Is there any other value of x where we know the value of a? Think back to this picture. Is there any value of x where we know the value of a? Aha! What about x equals -1? Does a of -1 have to be 0? It sure does. That's another property of integrals. The integral from -1 to -1 of anything is 0. So now we have an initial condition that will allow us to evaluate the arbitrary constant c. We substitute in the fact that a of -1 is 0, and the arctangent of -1 is negative tau over 8, or negative pi over 4, and therefore c must be tau over 8, or pi over 4. And that tells us that the function a of x is arctangent of x plus tau over 8, and now we can finally evaluate our original integral. A of 1 equals tau over 8 plus tau over 8, which is tau over 4, or pi over 2. And tau over 4 or pi over 2 should seem like the right number to you, because if you recall, when we were summing Riemann sums, we were getting numbers near 1.57. So we've now found the exact value for this limit of a Riemann sum without actually taking a limit of a Riemann sum. We found it by using antiderivatives, and it's going to turn out that we can find the value of any integral by using antiderivatives. So let's do the general case now, and when we do the general case, we will be deriving the fundamental theorem of calculus. We start out by saying, here's what we want to find. This little orange diagram at the bottom. The integral from a to b of f of x dx. We're going to define an area function to make this a bigger problem. We want to find the integral from a to x of f of t dt. The second orange diagram at the bottom represents the area function capital A of x. We're going to set out to find that, and then if we can find this function, then all we have to do is set x equal to b to find capital A of b, and we've got our answer to our original question. So how do we find capital A of x? Well, we start out by finding the derivative. And the derivative is the limit of a difference quotient. And the difference quotient has this integral. It's the difference of two integrals. It's the region in the third diagram between x and x plus h. It's that region divided by h. That would be the difference quotient. So the limit as h approaches 0 of that little region over h is going to be our derivative. The next step is to replace that region with a rectangle. If you look very carefully, you'll see the difference between this diagram and this diagram. Here I have the area under the curve, and here I have a rectangle. And making that change actually will change the value of the numerator of this expression, but it won't change the limit. So we rewrite it as the h times the height of that rectangle is the rectangle area, h times f of x. And then we can easily calculate the limit. And we have found that a prime of x equals f of x. Now remember that when we find the derivative of something, we still need an initial condition. So let's define capital F of x as being some antiderivative of little f of x. Then if a prime of x is equal to f of x, we could say that a of x is equal to capital F of x plus some arbitrary constant. And we need an initial condition to evaluate that arbitrary constant, so we use the fact that capital A of little a is equal to 0. And plugging in that initial condition, I get that a of x is capital F of x minus capital F of a. Now I've found the answer to the big problem. I've found the function a of x. All I have to do is plug in a of b, and that's the integral from a to b of f of t dt, which is the same as the integral from a to b of f of x dx, which is equal to the answer, capital F of b minus capital F of a. This is the important result. We've figured out how to find any integral, the general integral from a to b of f of x dx. The integral from a to b of f of x dx is f of b minus f of a. This is one way of stating the fundamental theorem of calculus. So let's actually state the fundamental theorem of calculus formally. First, I'm going to state it informally. The fundamental theorem of calculus informally says that integrals and derivatives are backwards processes from each other. Integrals are antiderivatives, and derivatives are anti-integrals. Now, to write that in formulas, we would say the integral from a to b of a derivative of f with respect to x is equal to the function f evaluated at b and a and subtracted. Okay, that's the result I was just highlighting. So this is the statement that says integrals are antiderivatives, because the integral of a derivative gives you the function back again. The second way of writing this is that derivatives are anti-integrals, so that if we take the derivative of this function that we made up, which was an area function, so the derivative of an integral gives you the value of the function inside. Okay, so we used both of these forms. We actually used this form first, and then from that we came up with an initial condition and we found this form. Those are both forms of the fundamental theorem of calculus. Sometimes they're called the first form and the second form, or sometimes they're called the first fundamental theorem of calculus and the second fundamental theorem of calculus, but they're really stating the same thing. They're stating that integrals and derivatives are opposite processes from one another. So the first thing we will do with the fundamental theorem of calculus is use the first form to actually compute some specific integrals. Our first example will be, suppose we wanted to know the integral from 0 to 1 of x squared plus 1 dx. That's this little region under a parabola shown here. I know from the fundamental theorem of calculus that this is going to be capital F of 1 minus capital F of 0, where capital F is an antiderivative of x squared plus 1. And I could find an antiderivative of x squared plus 1 just by using the power rule in reverse. Remember, we don't need the plus c here because it just has to be any antiderivative. So, therefore, the integral from 0 to 1 of x squared plus 1 dx is f of 1, which is 4/3, minus f of 0, which is 0. It turns out it's 4/3. So we have just shown that this area under a parabola, this little orange region, is 4/3. Let's look at another example, a little more sophisticated. Suppose we want to find the area under one lobe of the sine function, the integral from 0 to tau over 2 of sine of x dx, or the integral from 0 to pi. It's this orange region over here. Well, we know that that's going to be f of tau over 2 minus f of 0, where capital F is an antiderivative of the sine function. So let's let capital F of x be negative cosine of x. Then the area under one lobe of the sine function is negative cosine of pi minus negative cosine of 0, which is equal to 2. We've just found that the area under one lobe of the sine function is 2. You cannot find that out without the fundamental theorem of calculus.